Zoe Kourtzi from the psychology department here, talking about AI for mental health.
Great, thank you very much, Florian, and thank you, Carola, and the organizers for inviting me to speak today. I've been meaning to do that for some time, and the reason I haven't done it so far is that primarily I have questions rather than solutions for you today. So please speak up. I'm Greek, so I have no internal timing, but Florian is German, so he will keep me to tick, okay? He'll make sure I won't overrun. So I'm a neuroscientist, and I like looking at the brain and understanding behavior and understanding what happens when the brain undergoes damage or disease, and then behavior and cognition fail. And so the problem I want to talk to you about today relates to the broader issues of mental health, focusing primarily on dementia. So I'm sure you all know dementia is really the disease of the times, affects a very large proportion of the population. Currently, we are talking worldwide about 50 million people, and already in the UK, the costs that we have to deal with are accumulating to 25 billion. Is a very big societal and health economic problem. So how can we tackle it? What do we understand about dementia so far? There's been a lot of work in terms of animal models and studying patients to understand what are the markers for the disease. And despite the fact that we don't have disease-modifying treatments yet, we have a pretty good understanding of potential markers. So this is the interesting Jack diagram that shows progression of stages in dementia. So starting from what we call cognitive normal, where we don't have any cognitive symptoms, and then moving into this kind of gray area, which is mild cognitive impairment, or MCI, where we start seeing signs of cognitive impairment that could be due to pathology or not. And so this is really the big question. Before we have evidence that a patient has progressed to dementia, for example, Alzheimer's disease, and because there are different types of dementias, we go through a stage which potentially is early enough to diagnose and intervene, but we are very much unsure of which are the patients that actually will develop the disease, will express the pathology, and which are not. And obviously, this has huge implications for the patients themselves, but also for health economy, because a lot of money can be spent here through putting patients through all sorts of invasive and time-consuming testing. But also, this might be the zone where it's quite high risk for failure for clinical trials, because if the patients are not properly diagnosed and they go into a clinical trial, then the clinical trial might fail because these individuals might not have the pathology that the drug is targeting. So this is the space we are working, and effectively for the work I wanted to present you today, we are focusing in this kind of gray area of patients with mild cognitive impairment. These are patients that have been referred typically to memory clinics because they have some symptoms primarily relating to memory difficulties. So what is the problem when we try to diagnose patients at early stages? The first thing is patient heterogeneity. So we suffer from the fact that when we look at a large population of patients diagnosed with MCI, in fact, there's quite a lot of different individual cases. There's a lot of comorbidities, so they might not have the dementia pathology, but they might have cardiovascular disease. They might have depression. So not only pathological comorbidities, but also other mental health comorbidities that give the profile, rise the profile of a patient that has memory deficits. The other issue that we are struggling with is that our data is sparse. Usually when we look at, for example, research cohort studies, we won't have data collected on all the individuals from many different modalities that can be predictive. And also a lot of the measures that we need collected on individuals when they come to a memory clinic or in clinical practice in general are costly and highly invasive. So at this point we know, for example, that tau can be highly predictive, but to measure tau you need reliably, you need PET scans, therefore you have to rely on radioactive tracers. Not every patient can undergo this, can tolerate this. So we've got quite a lot of issues to deal with when it comes to really precise diagnosis as early as possible, and also some personalized diagnosis, which is really important. So we have taken the approach of looking at larger scale data. Primarily the data I'll show you today come from cohort studies or from research studies rather than from clinical work. And looking at how we can approach this through mathematical modeling and through machine learning to be able to make predictions as early as possible and as precise as possible. And we haven't done this alone. We've done this together with a large team of clinicians and with computer scientists. So quite an interdisciplinary effort to work on this data. And our aim primarily is to develop systems that are transparent so that we can understand the features, we can understand the predictors of the disease, and they're interoperable. So one major, again, challenge is we might build our models on one specific patient cohort with thousands of individuals, but does it generalize to the 50 patients that will come to the Cambridge Memory Clinic or to any memory clinic along the country? Can we then look at these individual patients and make predictions about them while we have built our machine learning model on a patient population that comes from a completely different demographic and has been measured potentially with different tests or had scans with in different scanners in different imaging centers. So it's really important to be able to look at, develop our models to be transparent and interoperable. And of course, what we target is early precision diagnosis. I'll show you work that we've done on MCI and some very, very recent work that we are doing looking much earlier, as we say, preclinical or individuals that are asymptomatic. We are very much interested in precise patient stratification. This is obviously very important for clinical trials. And we hope that this will help us move into the space of personalized interventions. And ideally, we want to be able to develop models that are trained, they're trained machines and engines, so that when we go back into the healthcare system, these new patients do not need to undergo all of these invasive and costly tests, but potentially through our research, identify specific predictors and test assays that are much less invasive and costly. So let me tell you what we've done so far. So as I said, we work with a large-scale cohort, ADMI, which is a population tested in the US across 5 different sites. These individuals have a lot of data collected on them. It's a research cohort study. We look at their cognitive data and the brain imaging data. And if you look through the cohort, you have individuals, they have clinical labels, so they're identified in this kind of, if you want, large subgroups. We have healthy individuals. We have MCI individuals that they're split based on clinical labels on 2 different subgroups. We have stable MCI and progressive MCI. The way that they are identified is progressive MCI individuals are individuals that within a 3-year window of clinical observation, their diagnosis has moved from MCI to AD, to Alzheimer's disease, while the stable MCI are individuals that within this 3-year clinical window of clinical observation, their diagnosis of MCI has not changed. So we work in this space, and the first problem that we identify is the problem of misclassification. So as I said, the way that these clinical labels are assigned is rather arbitrary because they depend on a window of clinical observations, of clinical assessments. And in this case, 3 years is kind of the cutoff. So a patient who within 3 years consistently had a diagnosis of MCI will be characterized as stable MCI, but could be very close to the class boundary to progressive MCI. How much different is really this patient from a patient that has switched to AD and is now in the class of progressive MCI, but very near to the class boundary. So a problem of misclassification, a high risk for that. Another problem is individuals that might actually fall in the same category but have very different trajectories. So we have to deal with this problem, and I'll come back to it when I show you what is the solution that we came up with. So what do we do? The approach we'll present you today was really motivated by building a transparent modeling approach, and therefore we took two steps. One is we looked for feature generation, and then we looked for machine learning algorithms based on a framework that is low parameterized, so we're using metric learning in this case. And the first thing we do is, as I said, we have cognitive data, and we look at data that have to do with patients' capacity for memory, for executive function, and for depression. These are our cognitive data. Then we look at their brain imaging scans, and we start with something very basic and hopefully the cheapest and non-invasively possible measure, which is gray matter. This is collected by a 5-minute T1 scan that is typically done on the NHS. So we are taking data that is as non-invasive and as cheap as possible. And what we do is, through a PLS regression model that we have optimized, we look into the brain and we look for features in the gray matter that predict memory decline to start with. And we also look at amyloid, and we look at tau. I'll show you how we do. Then we integrate all of this data into a metric learning model, and we look at predictors, but we also extract metrics out of our model that allow us to make continuous predictions based on longitudinal data. So that's kind of the overall framework. I'll take you now step by step. So as I said, we first start with gray matter. This is collected through anatomical scans. All of these patients have these anatomical scans, and we are looking at this window of MCI. So what we do is we use a partially square regression analysis, and we look at features in the gray matter that predict the scores that the individuals in this cohort have from memory performance. These scores are measured through different experimental tests, through different scales. We create a composite for this, and we look at features that predict, from gray matter features that predict their performance, their memory performance. Then what this method allows us is to take a new patient, take their gray matter, times it with our feature, and effectively make predictions for a new patient that was not used when in our training set. And that's what you see here. You see actually that the features that we extract are very much close to areas that we know are targeted by dementia. So they are in medial temporal lobe. We find them primarily in the entorhinal cortex, amygdala, and hippocampus. So this for us, when I first showed this to our clinician collaborators, they said, oh, no surprise, of course, this is where the disease hits. But for us, it was actually verification and validation that our methods are picking up biologically relevant features that are also relevant for the disease. So these are the features that we work from the gray matter. What do we do next? Right, so yeah, I should say that we go through a validation procedure. What you see here is the data that we use to extract the feature from the gray matter. So this is a large number of individuals from ADNI. And you see that the gray matter score that we extract from the PLS modeling predicts their memory performance. But then what we do is we went to John O'Brien and to James Rowe and to Sue Lee and said, do you guys have any data that do not come at all from ADNI? They don't come from the US, but they come from our local memory clinics. And they kindly gave us data from their own cohort study, Nimrod, which you can see it's much smaller. What we did in this case is we took the gray matter from these individuals, we put it into the PLS, and you can see that it predicts now memory performance in these individuals. And if you read the small print, you will see that actually these individuals have their memory performance measured with a completely different scale than the ADNI. This is actually a clinical scale rather than a detailed, if you want, a battery of tests addressing memory performance that is given to cohort studies. So we start building evidence that actually this feature is generalizable, and we believe this is because it is a feature that relates very much to disease pathology. So what you see here is another thing that builds kind of, confidence to this feature, is that if you take this score that we extract from the gray matter with PLS, you can see that actually predicts also tau. Again, we know that tau is related to disease pathology, and effectively what we have here is a gray matter score that relates to memory performance and to tau-related pathology, so a quite valid clinical feature. What do we do now? We have a gray matter feature. We have other biological data. We have, for example, amyloid. We have APOE4 also from these patients. And we have, as I said, cognitive scores, not only for memory, but also their executive function, so their capacity to attend, to make decisions, and also for depression. We take all of these features and then we put them in a metric learning algorithm. It's very low parameterized, nothing like the exciting things that we've seen earlier today on deep learning. But it's a very kind of transparent algorithm that we can interrogate. Effectively, what we do here is we have each class represented by a prototype. In fact, we've done it with multiple prototypes, but just one prototype, so a very linear algorithm will do the job. And what we do is we let the prototypes move every time that we put in training data and represent separable classes. So this is very much a binary classification of, is a patient stable or are they going to progress? We look at the MCI population. We ask whether our metric learning algorithms can separate them to stable versus progressive. And as I said, we give all of this biological data, our PLS gray matter, the amyloid, and the APOE4. And what you see is that the algorithm does quite well, about 80%, and not 95. There are deep learning models out there that they will do 97%. But the nice thing here, because the way the model is structured, is we can interrogate the tensors, and you can see very clearly what is the contribution of each one of the predictors that we put in to the model. And what you see is the beta amyloid is actually a very strong predictor of separating the classes, and also the PLS gray matter. So as we move on in our analysis and in our modeling, then we will use these two as very predictive features. We also do the same thing using only cognitive data. This is the biological model I showed you. We built another cognitive model. Again, same metric learning model. We asked the model to separate the progressive from the stable. And what we use here is ADNI-MEM is this memory score. Then this is the executive function. This is the GDS is a depression scale. What is interesting here is the patients actually have been screened for depression, and patients that had severe depression were not entered in this cohort. However, we still have depression scores that vary. So what we see here from the cognitive model is the cognitive model does actually equally well. If you look at specificity and sensitivity of the model. So not that much different from biological model. If you want to make pretty much, if you want binary classification, a fairly basic and crude binary classification, you can just use cognitive data. You don't need to go into the brain at all, or in any biological markers. And you see that clearly the memory and the executive function are the key features for predicting the two classes, separating the two classes. What is interesting is, again, if you interrogate a little bit more this data, what you see is that the biological data, in fact, and that's here, allow us to separate the classes. But effectively what they tell us is that the normal people, the people that are still cognitively normal, and the stable MCI people are very similar. So when we look at the biological model, we see that the stable MCI people do not have pathological features, right? They are very much different from the progressive, but the biological model tells us that they don't have pathology. Once we start looking at the cognitive, what we see is that, in fact, where they are separated is their cognitive performance. And when we start interrogating memory, executive function, and depression, what we see is that it's actually the depression scores that separate the stable MCI from the healthy normal. Now, this really brings again the misclassification problem into the picture, because what it tells us is that these stable MCI patients don't have the pathology, so they should not be going down a diagnostic and a potential treatment pathway that is the same as the progressive MCI individuals that have the pathology. In fact, maybe they have something else. Maybe they have some depression, and maybe they should be going down that diagnostic pathway where we try to understand better other comorbidities and that we can potentially treat. So again, I think a very important problem in terms of being able to interrogate the data and the features that we extract for dealing with this problem of misclassification and effectively difficult diagnosis problems. How else can we deal with misclassification? In our hands, this is a very difficult problem, and we thought that, in fact, these binary classification methods, so the metric learning approach that I showed you so far, is prone to it. So we do have the risk of individuals that are very close to each other, but they appear to fall in separable classes. So to address this problem, we went into an approach that actually looks at longitudinal data and at continuous data. So what we did is we did away with the classes. We put all the individuals, the data we have from these individuals, and what we wanted to predict is changes in their memory performance over time. Now, the individuals in this cohort in ADNI have been followed for about 15 years now. So we are fortunate to have data over time and through different assessments. And we have gray matter scans over time, and we have their cognitive data assessed over time. And what we can do from our metric learning model is we can build a scalar projection score. This is, in very simple terms, and we can talk about it later, is a score that tells us how far each individual patient is from the healthy prototype. So in fact, the stable, not the healthy, the stable MCI prototype. So for each patient, we can extract this projection from the stable prototype. And so we have a continuous metric that then we test whether it can predict changes in performance, changes in cognitive decline. And that's what you see. We can generate this scalar projection score from our metric learning model when it was built on cognitive data or on biological data. And what you see here is that how far each patient is from the stable prototype, the stable MCI prototype, relates to memory change. The higher they are, the further away they are from stable, the higher the decline they have in terms of memory. And you see, we can do this with cognitive data, we can do it with biological data, and if you look closely at these R values or the slopes of these regressions, what you see is that, in fact, adding biological data into the model now starts helping. So when we move away from kind of the crude binary classifications into a modeling approach that allows us to model disease trajectory, what we see is that putting in biological data like the gray matter feature and the amyloid, we've seen that they are highly predictive. We can do better in predicting future rates of cognitive decline. What else can we predict? We can also predict changes in atrophy, in gray matter atrophy. So not only changes in cognition, but change in biological markers like gray matter atrophy in the brain through the scalar projection. And we can also predict changes in tau accumulation over time. So having this longitudinal data really helps. I think I didn't say that all of the data that we trained the model is data at baseline. So it's not longitudinal data. What we do here is we use the data at baseline, we get our scalar projection, which is the metric that tells us how far each patient is from a stable MCI, and we predict about their future memory capacity and their future gray matter decline and tau accumulation. Now, how do we know this is valid? We built this on ADNI, and we used data from ADNI 2 to build the model, and there's another phase in ADNI, ADNI 3. So now we train the model on very different data, and we test, and you see that we get very, very similar predictions when we put in individuals that we haven't trained the model on. However, this is still ADNI data. This is data of a specific population demographic, data collected on the same centers. We came back to our Cambridge clinician collaborators and looked at the data they gave us, and what you see is that from data, again, from completely different demographic scanners, everything, we can get reliable predictions for longitudinal changes. In this case, is for memory performance over time through, again, a very different memory test. This is a standard clinical scale, the ACE3, on which patients' memory capacity is measured over time. And you can see that we can make predictions now for very few patients. This is a very small number of patients, about 30 patients in this sample, for which we could not build the model on. So it's not enough data to train, but it's actually quite reliable to predict, suggesting that really our features and the modeling approach is generalizable, it's interoperable. Now, even more exciting, and this is really the latest couple of slides, and this is very much work in progress. Where we want to go is patients that actually have volunteered themselves for research in this case, but do not have symptoms. They are in their 40s in this case, and they don't have any memory issues. But they volunteered for this cohort at Berkeley. And this is through our collaborators in Berkeley who released the data to us. And what you see here is we don't train the model on them. We have the model ready. It's a trained engine on the ADNI data, all of what I described to you before. We take the data of these asymptomatic individuals, and we ask how close the data is in this to this stable prototype, and that's what we plot here. And then we predict changes in amyloid beta for these individuals. This is one of the markers we have in this cohort, and you see that we can clearly predict that the further they are from the prototype, the higher the accumulation. We're still working on this data. It's very much work in progress. Another thing that we are trying to do is predict not only beta amyloid accumulation, but tau accumulation in these completely asymptomatic individuals from their baseline data. So they come into the cohort study, they are healthy, they have baseline tests, and from these tests, we, having built the model already, we predict the tau accumulation. And that's the very last slide. This is what we can do for asymptomatic individuals within ADNI, which is where we built the model. And this is what we do with a very different cohort of asymptomatic individuals. We can predict tau accumulation regionally in different areas. And you can see that our sort of higher predictions are actually in areas, again, middle temporal lobe, where we know that are hit by disease. So I'll close here and quickly summarize. I hope I've given you sort of an insight on the issues that we face when we try to do early disease prediction, especially in areas like dementia, where we have a lot of heterogeneity, a lot of subtypes, a lot of comorbidities that might cause misclassification. As I said, we took a very simple linear metric learning approach, and we developed features that are transparent and interoperable, and we try to move away from binary classification to the prediction of disease trajectories, the modeling of disease trajectories, so that we can actually be able to make predictions about individuals. And our strive is really to be able to move in making these predictions of individualized trajectories of disease as early from asymptomatic stages, not only from mild cognitive impairment stages, and with tests that are as less invasive and as costly as possible. I'd like to close by thanking you for listening. I very much welcome any feedback, questions you have. We can only make this hopefully better. I'd like to thank Joseph and Jan, who are PhD students in the lab working on these problems. our Cambridge and Berkeley clinical collaborators, and all our computer scientists. And of course, my lab, who makes this a lot of fun, and everybody who gives us money to be here. Thank you.
Thank you very much. Questions, please. Yes.
So can I just ask you, clinically, how are you excluding progressive cognitive decline due to progressive vascular dementia? Is that because you're not getting the MRI changes on the C1 scans, or how are those excluded?
This is before we get to the data, if you want. So this is all done through all of the tests that they are in the research cohort, and through the MRIs. So we get the labels already, so we know that vascular dementia is excluded in this case.
So have all the patients that you've looked at, have they all had their beta amyloid and their tau proteins measured?
Yes.
How's that done? Is it with PET? Or?
Yes. So there is data also with CSF, but the data that we use here is all PET data.
So they've all had a lumbar puncture as well?
Not everybody, I think.
CSF then?
Yeah, so that's why we don't use that data. So the data I showed you here is data from PET.
Okay, so they've all had a PET. They just have one PET, or they?
They have multiple PETs, so that's how we can predict tau.
From which they get the quantitative measure?
That's right, yeah. So we use SUVR, for example, normalized to cerebellum in this case. That's the data we use. But it's a very large cohort that has undergone sort of, if you want, different stages. So obviously the protocol has remained mostly the same, but there've been a lot of kind of changes, upgrades. For example, one of the key things here is patients, when they first started, were scanned on a 1.5T, later on a 3T. So it's actually quite interesting that the models can still predict, despite the fact that we have this great variability. Yeah.
Would I be right in thinking that the uncertainty interval, which is shown on your graphs about the regression line, is the uncertainty for the expected value?
Yeah.
But when you come to prediction, you have to include also the standard deviation for the prediction, and which makes it much wider. And that's why most of your dots are actually outside of your lines, because you're not showing the error for the prediction, you're showing the error for the expectation.
So I'll have to double check, but I think that I'll have to double check. It would be fitting very poorly. That's what, yeah, I'm trying to think. Yeah.
I was thinking about the bit at the end, the sort of early diagnosis bit.
Yeah.
So that if I understood right, then so you were predicting change in A-beta from what is basically a kind of structural measurement, which is kind of sort of counterintuitive a bit, because conventional wisdom is that A-beta change first, and then you see those structural changes later.
Yeah.
So is the implication there that it's something about the kind of normal structure that is predicting, that is identifying people who are more vulnerable, or is the implication that there is actually some early structural change?
Yeah. So I think it could be either. We don't know, because these individuals they clearly don't have any memory issues. So they've undergone all the tests as part of going into the cohort. So for us, we're sort of agnostic in terms of that's the nice thing about applying it data-driven rather than hypothesis in this case. As you say, based on what we know from the curves, that's the hypothesis. But also, the model has changed in terms of how we define AD, from going from these stages to a continuum. So obviously, there might be things we don't know, and it might vary quite a lot in terms of what cohorts we look. I think the model has been built based on patients that already kind of showed some pathology or some symptoms at least. So it will be very, very interesting really to interrogate this further and see. So we are trying to do this with the individuals from the Berkeley cohort studies, 200 individuals. So we're trying to do this with larger data sets to see whether we can effectively validate.
Also converters and
Yeah.
lots of
Yes, yeah. Yeah, so we can look at them too, yeah.
Thanks everybody. Let's thank Zoe again.
Thank you.